Does that work? Beautiful. Thank you. I'm Eric Mullen, and I'm here to tell you about verified peephole optimization in CompCert. So the great thing about verified compilers, such as CompCert, is this end-to-end guarantee they provide. The beginning of the input program that you give them is the same as this guarantee has been validated build verified compilers direct tension with more conventional C compilers. Deal with transformations at the high with assembly. An assembly transformation in its most basic and when its database of rewrites, it simply this. We might not get a lot of mileage out of this. Than any other part of the compiler. Today I present Peek. Correct peephole optimizations. This composes with the CompCert proof to give us first, there are these local proofs. Rewrite over an actual assembly program, is it however, we're not able to express a lot of the common peephole express these proofs. For one, we've built themselves correct. Further, we've built more operations over pointers, which allows us to first, these local proofs. In order to understand Sourav Bansal and Alex Aiken's 2006 paper on super So here we have a subtraction, a move, executed this, we can see something in arithmetic. Now, armed with this fact, so when we execute this, that the values in all of the registers are the same on both sides. X doesn't match. It's C. it's applied in a program where the ECX locally correct if execution through both sides produces identical. Now, the intuition behind what makes a people operand. And so we actually support you define a small matcher in tactics, which will a correct rewrite with that particular instantiation of registers. This register substitution. A meaning preserving transformation. Equivalent. Thankfully, specifically, we say that if we have some program state, then the program state in the transform program must now, in order to construct a proof of more than one instruction that we've rewritten. And so we have no great where we allow one step allow ourselves to match a single step on the left to walk through the proof of meaning preservation. Values in registers, same values in memory. We're good. However, as soon as still to the state in our transform program at once it steps outside the transform region, reestablishing matching on values and proceed on. Specifically, we needed this simulation entry and single exit properties, as well as some others. The program in which you're rewriting that has nothing to do with that we can never jump to the middle. And so if we've jumped into the middle, we have Now here we have a slightly different example. We have a jump. Turn it into a decrement followed by some knobs because the jump. Okay, to perform this rewrite in this program. First occurrence of label 1 in the function, specifically. Now, once we have all these properties, so now we have a sound. And in order to increase its expressiveness, we've built this. So if we take a look back to our example, are many ways to do certain operations. This is just adding ECX. However, LEA doesn't write anything to the flag. So this rewrite is only sound when register in x86. You can move the constant 0 into that register. When encoded. And this is kind of because whereas XOR will write them as it's an arithmetic. To express the correctness of all of these, we've implemented a liveness analysis. A particular register be read before it's written at and say definitely no, then we know that it's dead at that. We've implemented this as an iterative workless style algorithm. And we verified it against the simulation style specification. States in the same program agree on all live registers. If one can take a step, then the other must also be able to take a step, and the results must still match. We verified this assuming facts about both where calls and returns send their control flow in x86, and also live and dead across these call and return instructions. Now, once we have this liveness analysis, we're able to express the correctness of, but we're still not done. Yet another artifact that lets us express the correctness. And let's take a look back. It turns out that with everything that we've built, not provably sound in CompCert semantics. The issue comes from the values in EAX. Back to our original motivation, minus y minus 1 was the same as x plus bitwise not of y. But it turns out that in order to prove this sound in this fact over 2's complement integers, we need the fact that x minus is not a y for the contents of these registers. The contents of these registers are these values. Value, an integer or a long, a float or a single, or a pointer. An address into a memory model, CompCert's memory model. It has both this block and this offset, which corresponds to memory as laid out. Specifically, some bytes within each block, and if you want to address a particular part of memory, you pass it 2, and that would refer to this byte in memory. To understand why this x minus y minus 1 is not the same as x plus bitwise is not the implementation of subtraction. Here we look at what, and I'll walk you through it, don't worry. If we have 2 integers and we subtract them, well, it's straightforward, not causing us any problems. If we have a pointer and we've been decrementing that pointer, so we just get far back in this same block but a different offset. Subtract another pointer. To CompCert, this is defined if these were in the same block, calculating a pointer difference, and then we get the, if they're pointers into separate blocks, this is undefined behavior. If we go back to our program, our original, in the case where both our original program is calculating an integer, it's subtracting it, decrementing it by 1. However, a transform program is trying to take the bitwise knot of a pointer, which is undefined. However, this is a correct peephole optimization. When we apply it, it works. It's published in Alex Aiken's paper, and it's certainly not wrong. So in order to express the correctness of this, we've implemented a new semantics for x86. We call it AlBassam bits, and it uses as CompCert, but we model these pointer operations, all pointer values down to their bit level representation before expressing any computation over them. In order to express this mapping, we have these and pointer surject functions. Pointer inject maps a high-level block offset down to the low-level represent that pointer, and pointer surject goes the other way. Pointer inject has the option principle, and surject has the option return type because we use it to model whether a pointer is valid. We axiomatize some behaviors about these. The specific behaviors are in the paper, and the high-level takeaway is that we're axiomatizing the behavior of the system. Every time that you allocate some bytes model, but in reality, we have to put that somewhere. And so this is a physical address. This has to work somehow. This is system-specific, and so we leave it as a specification. Now, in order to understand how these values work in our semantics, let's take a look at the path of a pointer value in its lifetime. When we get a pointer, say from an allocation, memory will hand us back some address of what we just allocated. Now, we're going to inject this down to the low level 30 represents it in our registers. Now we can do any kind of computation we want with it whatsoever. We can store this and bitwise not at anything. To use this as a memory address right before we're going to convert it back to its high-level representation to memory in order to point to a particular byte. Once we have this in the semantics, similar to the existing assembly semantics, proven that our semantics simulation with the original assembly semantics, these pointer inject and surject functions, as well as assuming the best guarantee we could have hoped for as we started an infinite memory model and compiled down to a semantic. Once we have this new semantics, correctness of the example that we've seen all along. How do we evaluate this work? First and foremost, we care about expressiveness. being able to express the correctness of as many different peephole optimizations. And so we took assembly examples from Saurav Bansal and Alex Aiken's 2006 paper on super optimizers and used them as a challenge round for verification. And we verified the correctness of all 6 of them. First, this example that we've seen throughout, we replace a subtraction. We can also express the correctness of this test followed by a conditional jump. We can turn this into a conditional move. We can turn values and registers into an exchange instruction. We can turn this conditional mask conditional move of 0 within the program text. That works. And all in all, we've so far with an average of 7 contrast nicely to the just under 30,000 lines to build the whole system. And we if you recall, 256 in his verified software toolchain used to prove some high-level cryptographic properties about CompCert. They were able to compile it down to assembly and preserve all those. When looking at the generated assembly code, we found this top snippet, which contains a redundant load. Form it and verify this transformation into this bottom snippet. With one other minor rewrite, gave us a 4% speed up on their benchmark. This is a single high-level property that they proved originally. Now, no research happens by itself, as well as the greater UW Pulse couldn't have done it without any of you. So,
from Imperial College London. Thanks for the excellent talk. In the talk,
yes,
I didn't quite understand the role of translation.
It's a little far back for me to scroll. When you write down a peephole, rewriter pass correct for a specific concrete. You don't want to write a proof for like X in this example with EAX and EDX. You don't want to write all those different abstractly once, and then when we have you implement a small little piece which we kind of validate that instantiation that.
So every time a peephole is applied during compilation,
yes.
I'm wondering what impact does that have on compile time?
Well, by that, because it is not very good. We end up rerunning a liveness analysis every time we perform a peephole, which is currently the dominant performance impact of compilation.
Okay. So compile time is low, is that true?
Yes. We believe that there is some low-hanging fruit in there that could make it much better, but currently it is not great.
Hi, this is Zhong Xiao from Yale University. So good stuff. I have a question about your memory model, which you converting these pointers to a single thing, right? I'm curious whether these arithmetic on these bit operation would change the bits or these control flags and so on. I think a pointer arithmetic on the pointers with the offset may not be overflow, but if you convert it to a single address, I don't know which address you convert to some kind of a extra proof obligation.
So CompCert has modeled all of these arithmetic instructions as writing to the flag. And in fact, the only instruction that writes defined values occurs directly before a jump.
Right, I remember.
Hi there, good talk. Bomis Sistani. You were talking about the example optimization, and you showed the C version of that versus the assembly, right? The expression that you were showing.
Yes,
right?
yeah.
Would this have been possible to do your proofs in C directly, and what would that take?
I mean, so I guess the higher level motivation here is that doing these optimizations over assembly gives us the ability to exploit a lot of architectural details that we wouldn't have higher up. For example, yes, we could do that in C. But for example, turning an LEA into an add instruction, like